Hello and welcome to this lecture. So now we are interested in the previous lecture we saw how to identify points where the function may hit a maximum or a minimum, okay, and now we are interested in the interval. Okay, so we also saw that the many functions on an interval, the function is maybe continuous, it's differentiable, and then how does it behave? Is it going down, is it going up, or is something else interesting happening in the interval? Can I do something if I know the point at A very well? Can I say something about what may happen in the interval? Things like that, the trends and all that are very, very important. So we need to understand how a differentiable function is going to behave in an interval. Okay, a crucial idea for understanding this is called the mean value theorem. Okay, it's a very interesting and very elegant result. Once again, very simple to describe, but it is very, very powerful. It's got tremendous, it will improve the use of the mean value theorem, connects the derivative to the behavior of the function very, very closely. Okay, and it helps you solve the increasing decreasing problem. It helps you solve the trends problem and all of that. Okay, predicting how the function is going to go and all that. Okay, so let's start and try and understand this. This section is going to be a little bit more technical, so I'll do a few proofs. Okay, it's okay if you don't follow the proofs entirely, but try to make an effort, because this is also at the end of the day a math course. So maybe you should learn a little bit about how these proofs work. Okay, but the proofs are not so important for the purposes of this course. You'll not be evaluated on the proofs. It's just for your understanding. Okay, so first of all, what is an interval, right? So we've been talking about this interval. I guess all of us have a reasonable understanding of what the interval is, but there's precise definitions here. So mostly these definitions of open, closed sets and all that come in an area called topology. We are not studying that at all in this class. If you're interested, you can look it up for further information. Okay, so here is definition and notation. There is the square bracket a comma b. Okay, this will denote a closed interval. Closed meaning this is the set of all x such that a is less than or equal to x, less than or equal to b. Okay, so if you were to look at the real line, x is the variable here, and it will start at a, end at b, and a and b are both included. That's what this, this sort of solid circle shows. This is the square bracket a comma b. This is a notation. It's just a notation. It denotes the closed interval. You also have the, the parenthesis a comma b. It's not square brackets, it's curved brackets, bracket a comma b, or just bracket, right? This is square bracket, this is just bracket. Bracket a comma b is a comma b open interval. Usually people say the open interval a comma b. Here, this is the set of all x such that a less than x, less than b. Okay, so this open interval includes all the points in the closed interval except a and b. Okay, a is not included, b is not included. So I've shown that by these open circles here. Okay, so there's also, like, partially open intervals. So you may have a square bracket at a and a curve bracket at b. So that's like, open at one end, closed at the other end. You can also do the other way around. Okay, so this notation, this being this curve bracket and a square bracket, denotes the open and closed, etc. Okay, so it may be open on one side, closed on the other side. So closed on the this side, open on this side. So it can go either way. But typically this closed interval and open interval will occur again and again when we look at continuous differentiable functions in intervals. Okay, so here is a couple of definitions. A function f from a comma b to r. Okay, so what do we mean by that? This interval a comma b, in that interval this function is defined. As in, for every point in this interval, I know how to evaluate this function. I will get some real number, but this point is this interval is contained inside the domain of f. All the values of x for which f of x is defined, that is called the domain, and this a comma b is contained in that domain. So f will take a comma b to some real numbers. Okay, so this f is said to be continuous on this a comma b, on this closed interval a comma b. It's very simple definition. If f is continuous at every point x in a comma b. So far we have talked about continuity with respect to a point, right? F is continuous at a point if, the any sequence that converges to that value, the f is defined in the same way. Okay? We had a definition for the point convergence, point-wise convergence of a function. So here, if this function is converging at every point in the closed interval, we will say if this function f is continuous in every point x on the closed interval, then we say the function itself is continuous on that interval. So this continuous on is that definition. So likewise, you can also have differentiability. Okay, So what is differentiability? Differentiability for a particular point involves limits from both sides, right? So there's this definition of f of x plus h minus f of x by h, and then h could be 0 plus, 0 minus, both have to exist, right? So there has to be function definition on both sides, okay? So differentiability usually works only in the open interval a comma b. Okay, the function stops at b, sort of, right? So you can't differentiate at b because you can't go to the right. Okay, so this is sort of one thing to keep in mind. If you define the function only between a and b, the derivative will be in the open interval. So you'll see always the continuity can go up to the closed interval, while the differentiability usually goes only in the open intervals. This is some small nomenclature differences. It's a bit technical. It's not too important for us at this point. You can just think of both of them as the same for convenience if you want at this point. It won't hurt you too much if you do that. Okay. But of course, it's a very critical difference. There's lots of things change between these two things. I'm just saying it because if you're getting confused by this, it's not so big a deal for engineering applications and all that. Okay, so let's say this is differentiable in AB if f is differentiable at every point x in the open interval a comma b. Hopefully, you see here the subtlety between why I'm not including the point b here. Okay, so that just complicates the derivatives and all that. Okay, hopefully this definition is easy enough. So the function f, if you say it's continuous and differentiable in some interval, then it means basically that the function is very smooth. You can draw it without lifting the pencil, and then no sharp corners also, right? If you have a sharp corner, then that function won't be differentiable there. So basically this is just modeling a continuous differentiable function between 2 points. Okay, and it's continuous everywhere, differentiable everywhere in that interval. Okay, there's a subtle difference between open and closed, but we'll just be loose about this. We'll just say interval. Okay, so a function is continuous and differentiable in an interval. What can we say about it? Okay, so let's just think about continuous functions and intervals. So here this is a nice picture, a simple question that I want to ask. Let's say f is continuous on an interval a comma b. What happens to an interval when f is applied to it? Or, so we've been looking at x belonging to this interval a comma b. If I look at this connection, the set of all f of x such that x is in AB, how will this look? Okay, so let me show you an example. Here's an example. Okay, so this is a little video, it's an animation. I'll animate it, I'll stop it and show you. But here's the starting point. This red is a function. Okay, so some function. It's a continuous differentiable function. And I have my AB here. I hope you can see it. This A is the starting point of this interval and B is the ending point of this interval. It's a little bit dull here, but hopefully you can see it's between A and B here. Okay, so this is the interval, and the function starts here at A and then rises, goes up to the peak and then falls again and stops here at B. Okay, so this is the function, okay, between A to B. So if you focus on A to B, you have just the function from here to here. This is the shape that you'll get. That's the black shape that I've drawn here. Is that okay? The overall function may be defined for all real numbers, but I'm focusing on this interval AB. So what happens to the interval AB when the function f is applied to it? It goes to another interval. Okay, so that's what happens to this function. Okay, it turns out all continuous functions do that. If the function is continuous from AB, then an interval AB, that interval AB will go to another interval between the minimum value and the maximum value of that function in that interval. Okay, so in this interval AB, this is the minimum point. So what I'm going to do, I'll play this video. This video will shift this interval. This interval AB will keep shifting now, and you will see that this min f max f also keeps changing, but nevertheless it always is an interval. Okay, so let's see that. See, notice here. So I'm just stopping here just to show you. Here's another interval AB, and the function goes from min f to max f. So let it keep going. I'll let it stop here also. So here again you see, maybe this is a little bit more clear. You have AB going to min f to max f. So notice the shape of the function here, it has changed, but an interval goes to an interval all the time. So let me just let it run for a little while. So you see here, here's another point A, B. Here the function has gone negative, but nevertheless, it goes from min to max. Okay, so here is, I hope you see it. All sorts of interesting things here. Look at this part of the function, right? AB is an interval here. this function, the black part is going from min to max. Again, the min f and max f remains the same. So as long as AB keeps sliding along and you go to the function, this f of x given, f of x in the range for x in the range AB also ends up being an interval. Okay, min f, max f. So notice here, let me just play the video out for you. It's an interesting little animation to look at. So that's it. After that, it just traces back. You can see what it is. Okay. So this and this sort of visually, I hope you're able to convince yourself that an interval will take a continuous function will take an interval AB to another interval between min of f in that interval and max of f in that interval. Okay. So this is a very important result. So f of x for x in AB in a closed interval AB is actually another interval. Okay, that interval is min of f of x for x in AB to max of f of x in x in AB. Okay, the minimum value of f in that interval, maximum value of f in that interval, f takes the AB to this new interval, min f to max f. Okay, so basic idea is a continuous function f takes an input interval to an output interval, closed, right? Input closed interval to an output closed interval. So this is closed, this is also closed. What does it mean? So the min and max are actually achieved at some points in the interval. So notice this particular point here. So maybe I should let it run for a little while. I'll show you. Okay. So you see here the maximum value of the function in the interval AB is achieved somewhere here, right? So this value of x, I don't know what the exact value is. So some particular value here. The max f is attained. The min is attained at the edge. Okay, at the end, right, at A. So, but if you run it further, you'll see at some point, you know, the min may also be achieved at something it's not. See, now if you see here, the minimum is attained somewhere in the middle, maximum is attained at the end. Okay, so both may also happen. It depends on how quickly the function is varying and how wide your interval is. Both the min and the max may not be at the end point. It can be in the middle also, right? But nevertheless, the min will be attained, max will be attained. Okay, so in the interval, min and max are attained. Okay, so this is a crucial result, and we will not prove this result in this class. The proof is very technical. In fact, it appeals to one of the basic axioms and of real numbers and all that, which we are not studying formally here. So we'll just accept this. Okay, so a continuous function is going to take a closed interval to the min of f in that interval, comma max of f in that interval. So minimum and maximum are both attained in the interval for a continuous function. Okay, so I hope this picture is sort of convincing to you. Okay, so you see that's how it works. Quite often min and max may be both the endpoints also. So here in this case, B is the minimum value, A is the maximum value, but that is not true, right? So for instance, if you see here, A is here, B is here, max is attained somewhere else in the middle, min is attained at the endpoint. So, but if you increase the B all the way to here, for instance, if A and A were here and B were here, then minimum is attained here, maximum is attained there, f will go from min f to max f. Okay, so various different possibilities are there, but still the important idea is in the closed interval, a continuous function achieves its minimum value and maximum value inside that closed interval. Okay, an important result. We'll just accept it and use it. It's sort of intuitive, you know. I mean, you have a pencil, you're just drawing the curve. You're not allowed to lift the pencil. You're not allowed any sharp corners. What can happen, right? It has to go from min to max in the interval. Okay, so that's the idea. Okay, so once you accept this, a lot of other things become very, very easy. Okay, so the next very interesting question you can ask if a function is continuous and differentiable is, supposing, say, some part in the middle of AB. So you have you know that this function f is continuous and differentiable in the interval AB, right? And you know a comma f of a, b comma f of b. Maybe somebody came off and erased the actual function between a and b. Okay, but you know it's differentiable and continuous. That's not a problem. But somebody just erased the function between a and b, and now you have to sort of wonder what all could be between a and b in the interval a b. How could the function look? What are all the possibilities? Are there some interesting conditions? Okay, so this is what mean value theorem is all about. Okay, so it sort of gives you an idea, some interesting property for however the shape may be, as long as you have to draw continuous differentiable curves, there are some very interesting properties that are satisfied. Okay, so graphical answer. What is the graphical answer? You just take a pencil and draw smoothly without lifting the pencil. But there are a lot of possibilities, right? It's just you can draw like this, that, you can imagine, you can just take the pencil and draw any which way you want, okay? But the interesting question to ask is there anything particular you can say, no matter how the shape may be, some property has to be satisfied, okay? Mean value theorem tells you that, okay? So it's a very, very powerful idea, okay? So is there any connection? For instance, there is a line joining AB, right? Okay, this is not a differentiable. This is a possibility, right? The function could be this. It is continuous at A, continuous at B, and the line is differentiable in the open interval AB. Okay, so it could be this. This is one possibility, but there could be many other possibilities. It turns out there is one connection between this straight line and every other possibility that you can draw. Okay, the mean value theorem nails that down. Okay. So, I have given you enough of an introduction. Now, let us talk about the mean value theorem. But before we do the mean value theorem, we will do a special case of it, which is called Rolle's theorem. Okay, what is Rolle's theorem? It asks the same question except f of a equals f of b. So, in the previous picture, I had f of b being less than f of a, right? F of b was less and f of a was higher. But in this Rolle's theorem, we will assume f of a and f of b are same. Okay, what does Rolle's theorem say? Let us read it. If a function f is continuous in AB, on AB and differentiable in AB, basically continuous differentiable function in the interval AB, and f of a equals f of b, f of a and f of b are equal. And like I said, this middle part has been erased, you don't know what's in the middle, okay. It turns out whatever may be in the middle, there has to be a point C in the open interval AB such that the derivative is equal to 0, okay. So, here's a wonderful little property about sort of predicting what a continuous differentiable function can be. Sort of intuitive, right? So, if you have to have a pencil and you want to draw from A to B and f of A and f of B are the same, somewhere you have to have a peak or a bottom, right? You can't avoid it. You have to go up from A or go down from A and then, or be flat. If you're flat, then the derivative is 0 everywhere, right? If you're not flat, then, if you go down or you go up, then, you have to hit a peak and come back, because you're coming back to f of b and you're not allowed to lift your pencil. So, it's very intuitive that there should be a peak, okay, or a bottom, right, minimum value, and the Rolle's theorem guarantees that in a mathematically precise way, defines it and proves it mathematically precisely, okay. So, for a differentiable function in AB and f of a equals f of b, there has to be a point C in the open interval such that the derivative is equal to 0. Okay, so we're going to see a quick proof once again. We'll be very quick and okay. Anyway, before the proof, an illustration. So, for instance, I could have something like this, right? So, this is just I've taken a pencil and then I've drawn. It's not very precisely to shape, but you can see it is one possibility. And what Rolle's theorem tells you is that there is a point C in AB such that the slope is 0, right? So, that's what it's just an illustration of what the theorem is telling you. Okay. So, here's a proof. Okay. The proof starts with the previous result we had. The interval AB is taken to min f comma max f. Okay, min and f are over x in AB. I have not shown that explicitly here, but min f comma max f. Okay, I'll just quickly go through the proof. Like I said, the proof itself is not so important for us. I just wanted to do it to give you a flavor. Okay, if you're bored or scared, you can just skip to the video where the proof ends. No problem. Okay. So, if min or max, there are two cases to consider. Okay, min or max occurs inside the open interval. It does not occur at the end. Okay, so we saw in the previous example, in some cases the min, both the min and the max were at at different edges of the interval. Min occurred at one point, max at sometimes the min and max occurred in the middle, right? That also happened. So the first case I'm going to take is min or max. Okay, the min f or max f, one of those two occurs in the open interval, does not occur at the edge. Okay. Okay. So, if that is true, then f prime of c, that for that particular c, f prime of c should be 0, right? Why is that? Well, that comes from the local maxima minima theorem, right? If you have a min or a max, local minima, local maxima at one point, then f prime will be 0. Very, very easy, isn't it? So, you can find a c very easily if this min or max occurs inside the open interval AB. We are already done, the proof is done. But in case that does not happen, min does not occur inside the open interval, max does not occur inside the open interval, then what should happen? Min and max both should occur at either A or B. A should be min, B should be max, or A should be max, B should be min. Okay. right? So something like that were to happen. If that were to happen, but crucially what's happening, f of a equals f of b, right? So if min and max both occur at a or b and f of a equals f of b, what should happen? Min of f is f of a, which is same as f of b. Max of f is also that same value, okay? So if both min and max are equal, then what should f be in that interval? It should just be flat, okay? If it is flat, then of course f prime of c is 0 for all c there, right? So it's a flat line. Flat has got slope 0 everywhere, okay? So whatever may happen to this min of f, max of f location, you are guaranteed a point c such that f prime of c is 0, and that concludes the proof of Rolle's theorem, okay? Now Rolle's theorem is an important ingredient in mean value theorem, in the proof of the mean value theorem. So what is mean value theorem? So here the only thing we don't like about this is the assumption that f of a equals f of b, right? We can relax that assumption and you will get mean value theorem. Here is mean value theorem. If a function f is continuous on AB and differentiable in AB, then there is a point C in AB such that f prime of C is now not 0, but it is equal to the slope of the straight line connecting a comma f of a and b comma f of b. What is that? F of b minus f of a by b minus a, right? So that's the slope of this line, right? That connects this f of b minus f of a by b minus a, right? So that's the slope of this line. And there has to be a point C in between. In whatever way this curve may look between A and B, there has to be a point C between those A, B such that the derivative is equal to the slope of that line. Okay, so here is an illustration. Here is one particular way in which you may have drawn the curve between A and B, and there you see that there is a slope. There is a point C where the slope is exactly equal to this line, as in this tangential line and this line are parallel, okay? So this is the generalization of Rolle's theorem when f of a and f of b are not equal. Now of course, if f of b is equal to f of a, this implies the Rolle's theorem, right? So because it's f prime of c is equal to 0, so you get that. So this is mean value theorem. It looks a little strange. You may say, I claimed that this had a lot of usefulness and all that. It may not be obvious to you directly. What are you saying? You're saying something very simple about, if I join a point from A to B without lifting the pencil or without doing crazy things, then I have to have a slope which is parallel to this. Seems like a simple result, but then like I always say about how math works, right? You start with simple results, use more and more and more involved logic and build it into more complicated results. We'll do that as we go along in the applications of derivatives module. Okay, so here is a quick proof. Once again, the proof, if you want to skip, you can feel free to skip, but I'll put in the proof just for completeness. Proof is very simple and elegant. Okay, what we will do is convert this proof into a Rolle's theorem case. Okay, like I said, we did the basic case first with a very simple case. Then we are doing the next more advanced case, right? We'll use the basic case. We'll convert this into the basic case. So I hope you see that as we study more and more concepts, how the same idea, the mathematical deduction idea, comes over and over and over again. Use the basic result, and then the next result, the next result. Just use logic in between. Here is the crucial piece of logic. You look at a function g of x, which is f of x minus some rx. R is some constant. X is my variable here. G of x is f of x minus rx. And how will I pick r? I'm going to pick r such that g of a becomes equal to g of b. So you can write this down, right? G of a equals g of b. F of a minus ra equals f of b minus rb. Okay, right? That's g of a equals g of b. You solve that, you'll get this. It's a very simple exercise. Try it. Okay, so you'll say r is f of b minus f of a by b minus a. So now g of a equals g of b. You should be reminded of Rolle's theorem. F of x minus rx is also a continuous differentiable function, right? I didn't do anything strange here. I just subtracted one from the other, and continuity differentiability is preserved under these operations. It's a continuous differentiable function, and g of a equals g of b. So you use Rolle's theorem now. By Rolle's theorem, there is a c in AB such that g prime of c is equal to 0, right? But what is g prime of c? If you differentiate here, you're going to get f prime of x minus r, isn't it? So I'm sorry, f prime of c minus r. Okay. Now g prime of c is equal to 0, which means f prime of c is equal to r, which is what you want here. Okay. So this small little modification to the function makes it sort of the same. You do a linear adjustment with the rx so that the f of a and f of b become equal, and then you apply Rolle's theorem, which gives you the guarantee for the existence of a c. Okay, so that concludes the proof of mean value theorem. Once again, I want to remind you that this looks like a technical result, but it's not. It's a very intuitive result also. So however you draw it, there should be a point where the slope becomes parallel to the tangential line, becomes parallel to the straight line connecting uh, just a comma f of a and b comma f of b. This is a powerful result. Okay, it may look very ordinary at this point, but you'll see how powerful it is when we see specific applications. Okay, so this concludes this lecture. Hope you got a feel for how we took this definition of a function being differentiable and continuous in an interval and came up with this nice characterization of intervals going to min and max under the continuous function. And then once you have that, you're able to show that Rolle's theorem and mean value theorem. And as I promised, in the ensuing lectures, we'll see some fantastic applications of this result. Thank you very much.